So metabolism is the sum of energy spending and energy requiring reactions in the cell. Energy is needed to do work in the cell. It's kind of boring to call it work. You could call it play. It's really just to do stuff in the cell, but technically we call it work. But what we mean by that is movement, transporting things across the cell membrane to bring things in that the cell wants or to get rid of wastes, and biosynthesis or growth. So energy is required to drive any of those processes. Energy is not created by the cell. It's harvested from the external environment, often from the electron bonds between food molecules. So metabolism could be thought of as the reactions that harvest energy from the environment and then spend it to keep cell processes going. So it's the sum of all of that, the energy acquiring reactions from energy has to be acquired from somewhere. So the cell has all these energy acquiring reactions, and then these energy spending reactions to keep the cell functioning. There's kinetic energy. Okay, so there's two different types of energy. There's kinetic energy and potential energy. Kinetic energy is more intuitive. It's the energy in movement. And we know intuitively that there's energy in movement, right? Because we know intuitively that there's more energy in a mosh pit than in a room of students who are sitting at their desks, right? So in the classroom, there's not very much kinetic energy. In a mosh pit, there's a huge amount of kinetic energy. And we know that intuitively. If I asked you, where's there more energy, in this class of students or in this mosh pit, you would know intuitively that it's the mosh pit, right? At least when it comes to kinetic energy. So potential energy is a little less intuitive. It's stored energy. And so energy is stored in unstable situations. So potential energy is the energy in unstable situations, such as chemical or electrical gradients. So here's an example here. Well, the first example I have are just these rocks, right? So there's all these artists that like to build these sculptures of these rocks that are precariously balanced on top of each other. It seems like you just touch this with your finger and the whole thing comes toppling down, right? So there's all of this potential energy stored in this unstable arrangement of rocks. And that potential energy, it's stored, but it would be released if you perturbed it slightly, right? So if you gave the top rock a little bit of a push, perhaps the entire thing would come toppling down. But when we're talking about the molecular world, potential energy can be stored in unstable chemical gradients or electrical gradients. So gradients contain energy because physical laws of the universe drive everything towards random distributions, right? That was one of the laws of thermodynamics. So one law of thermodynamics, there's two laws of thermodynamics, and one of them is entropy is always increasing in a system. And remember, entropy is the measure of disorder. So that means that randomness, disorder, is always increasing in every system. That's the more stable state. So when you take away that randomness from a system, then you've created an unstable situation. So if you look here, this is not a random distribution of these red molecules, right? So it doesn't matter what this red molecule is. It could be an acid, it could be a salt, it could be a sugar, a gas, it doesn't matter. The point is, it's not randomly distributed. You have a high concentration inside the cell, and a low concentration outside the cell. So laws of thermodynamics dictate that this molecule is going to move from areas of high concentration to areas of low concentration, move out of the cell. This situation where there's a high concentration here and a low concentration out here, that is unstable, because it is not a random distribution. So until an equilibrium is reached, until you have an equal concentration on both sides of the cell, because this molecule was truly randomly distributed, there's going to be an unstable situation here. And that is stored energy. There's stored energy here because you can think of it as, an unstable situation as tense. This is a tense situation because you've stuffed all of these red molecule, whatever it is, sugar or whatever, you've stuffed it all inside this membrane, and there's not very much outside the membrane. There's a tension there because these are pushing to get out, right? And then, it doesn't matter which direction the gradient is, whether a gradient is moving from high to low, right? So high to low in this direction, or the high concentration could be outside the cell, and the low concentration could be inside the cell, you still have an unstable, high energy situation here, where the molecules outside the cell are pushing to get in. There's this tension because everything naturally is driven towards random distribution, which is fairly equal on both sides. Okay? So you can remember that there's this inverse relationship between stability and energy. So the more stable a situation, the less energy there is. The more energy in the situation, the less stable it is. Right? So there's an opposite relationship where energy is high, stability is low. Okay? So these chemical gradients or electrical gradients too. So an electrical gradient is just when the gradient is electrons, an electromagnetic charge, right? So if you have, when you have electricity in a wire, the electrons are moving down their gradient, their own gradient. You have a high concentration of electrons in one place and a low concentration in another place, and they move down their concentration gradient. Okay. So and then that electricity gives you energy, right? You can use that electricity to drive work in your house or play, right? Or whatever, just drive activity in your house. So chemical energy is a kind of potential energy. This is a molecule called ATP, and we're going to talk a lot about ATP in this chapter. ATP stands for adenosine triphosphate, and adenosine is a nucleic acid, and that includes, a nucleic acid is like RNA or DNA, and that includes this component here on the right. That's the adenosine. Adenosine is found in RNA and DNA. And then you have 3 phosphate groups on the left. This is the high energy piece of this molecule, these 3 phosphate groups. The reason it's high energy is because these bonds are very unstable. They're very unstable because you have a lot of electrons packed into a tiny space. And remember, all electrons are negatively charged. Opposites attract, but like repels. So there's all these negative charges repelling each other, but they're forced close together because each line here represents a pair of electrons. So you have 2 pairs or 4 electrons stuffed next to each other here, another pair of electrons here, another pair of electrons here, another pair of electrons here, and then all of these negative charges, which are further more electrons. So you've got all of these electrons packed together in this tiny space, and they're all repelling each other, but they're being pressed close together. That's tense. That is unstable. That is high energy. So there is energy stored in this molecule called ATP, and name is down here, or adenosine triphosphate. Molecules like sugar or fats or ATP contain energy because certain configurations of electrons are unstable. So, and again, that's because electrons repel each other, right? So electrons repel each other, but some molecular bonds force many electrons to be close to each other because of the arrangement of nuclei that hold the electrons in orbit. So this is very unstable, and when such an unstable bond is broken, the energy then is released. So I told you that one law of thermodynamics is that entropy is always increasing. Everything is moving towards a more random distribution. But the second law of thermodynamics is that energy is never created or destroyed. It is just converted from one form to another. So when you break off a phosphate from this molecule, there's a relaxation, right? There's less tension because you have allowed this clustering of all of these electrons here to separate, to space out. And that's a relaxation of that tension because they were all repelling each other. But that doesn't mean the energy, we've said where situations are unstable, there's high energy. You've now, when you break off a phosphate group here, you've made a more stable situation, right? So the situation is more stable. That means there's less energy in the molecules, but it can't just disappear. The energy goes somewhere. So the second law of thermodynamics is that energy in the universe is constant. You don't get more energy, you don't get less. There's always the same amount. Energy doesn't appear, it doesn't disappear. It just shifts from one form to another. And I know it's not intuitive to think that way because we usually think of energy as being able to, appear in our homes and then disappear. But in terms of, if you take a universal view, It's just changing forms. And so you really have to get used to thinking of it that way when we learn about metabolism. So you break off this phosphate group, the bonds relax, that repulsion between electrons relaxes, this situation increases in stability, decreases in energy. That energy is no longer in ATP, it's been released. And it's going to do something for the cell. So ATP is, we call it, it's like a battery. It's what carries energy to every place where the cell needs to do work or some activity. So the cell wants to bring a molecule in against its concentration gradient across the cell membrane. ATP is going to provide the energy from that by breaking off a phosphate group. Let's say the cell wants to build more cytoskeleton. The ATP is going to provide the energy for that building, because building is work, right? It takes energy to build something. So breaking off a phosphate group from that ATP and the energy released from that ATP is going to be applied to building more parts in the cell. Let's say the cell wants to move somewhere, needs some energy. Bunch of ATP go to whatever, whether it's cilia or flagella, or it doesn't matter which it is, but ATP is going to go there and drive those appendages that provide motility to the organism. And so again, ATP is going to provide that energy by phosphate groups are going to break off, energy is going to be released from the molecule, and the energy is going to be applied towards the movement of the cell, and so on and so forth. So you get the idea. So ATP, it is like a battery, but we actually call it the energy currency of the cell because it can be used in any energy requiring reaction in the cell. So let's talk about that analogy for a bit. So ATP is often called the energy currency of the cell in textbooks, lectures, things like that. So let's think about what currency does. It translates many different types of value into a single standardized system that everyone in a country can recognize and use. Energy currency like ATP translates many other types of energy to the same chemical form, which can be used in all energy requiring reactions in the cell. So let's think about this. So when we're talking about monetary currency, you have all different kinds of currency around the world. And in each separate country, that currency has value. It has an agreed upon value. It's worth a certain amount. But let's just say you work in retail, and let's just say your retail store, the store you worked in, had to be capable of accepting all the currencies of the world. So let's just say you worked in Santa Fe, where you get all of these tourists from all different countries, and you have to be able to sell your goods in every currency: US dollars, euros, Indian rupees, Thai baht, all of them. You need to be able to, that would be so bulky, it would be so unreasonable, right? That you would have to be a great math whiz to be able to calculate the exchange rate and figure out what your goods are worth in every single currency of the world. So we don't do that, right? Every time someone comes to our country, they take their many varied kinds of currencies, go to a bank, usually in the airport, and convert it to the US dollar. This is the currency that is good anywhere. And then this dollar can be used for recreation or getting, labor, getting work done, services, getting work done on your house, or food, anything. This dollar works anywhere. You can take, all of these currencies do have value, right? But they have to be converted into the currency of the local area in order to be used properly and efficiently. And same when we go to another country, right? We convert our US dollars to the local currency of wherever it is we go. So this analogy is perfect for ATP because there's all these different kinds of energy out there. There's energy in light, right? Photons have energy that plants can harvest. There's many different kinds of fats out there. There's many different kinds of sugars and starches, glycogen. There's proteins. There's so many different kinds of energy sources that we take into our body, even just us, that we take into our bodies. And if our cells had to be set up so that every single energy requiring process had to be able to use, it had to be set up so that it could use glucose or fructose or sucrose or lactose or galactose or this kind of fat or that kind of fat, right? Every single energy requiring reaction would be so bulky and huge and take up way too much space in order to be able to do that. So it's much more efficient for the cell to bring in all of these different kinds of energy and then convert them all into ATP. So take the energy from glucose. Glucose has energy, great, bring it in. Fructose has energy, great, bring it in. Lactose has energy, great, bring it in. Sucrose has energy, great, bring it in. Take the energy in all of those molecules, convert it all into ATP. Now ATP is the one energy currency of the cell that can be used anywhere, just like the US dollar is the one monetary currency that can be used anywhere in the US. So there's a few review concepts I want to go over before we really dive into metabolism. I want to go over redox reactions and phosphorylation because we're going to draw heavily upon these. So redox reactions, redox stands for a combination of oxidation and reduction, well, in reduction and oxidation, I guess. And those are just reactions where an electron is transferred. So we talked about how unstable electron configurations carry a lot of energy. High energy electrons can be moved from one molecule to another, and usually energy follows that. So energy tends to follow those electrons around. Okay. So redox reactions are really critical in understanding metabolism. How do we extract our energy from our food? It's usually by stripping high energy electrons, and that's going to count as a redox reaction. So redox reactions are when electrons are transferred from one molecule to another. Oxidation is the loss of electrons. Reduction is the gain of electrons. And I'm one of those people who just can't memorize stuff like that. So I have tricks that I still use to this day. It's like I know what a redox reaction is, but which one is oxidation, which one is reduction, I always have to stop and think. So I like to remember Leo, the lion, goes grr. Leo, L-E-O, L stands for loss, E for electrons, O for oxidation. Loss of electrons is oxidation. That's Leo. Leo, the lion, goes grr. Grr is G-E-R. Gain of electrons is reduction. Okay. You can also remember oil rig. Oil, O-I-L. Oxidation is loss of electrons. Rig. Reduction is gain of electrons. Right? So that's redox reactions. Phosphorylation. That's when you move a phosphate group from one molecule to another. And that's like what we were talking about with ATP. ATP had those 3 phosphate groups. When a phosphate group is broken off and maybe added to another molecule, it transfers some energy. Some energy is released. So there's 2 different kinds of phosphorylation. There's substrate level phosphorylation, and that's really simple. There's chemiosmotic phosphorylation, which is very complicated, and we'll get to that later. But the main thing is phosphorylation has to do with moving a phosphate group to a molecule. A phosphate group is a phosphorus surrounded by oxygens. All right, so let's talk about redox reactions that will be important for metabolism. So there are these electron carriers, and their job is to facilitate redox reactions. So they strip electrons from one molecule and give them to another molecule. So when they take electrons from something, they oxidize it and they become reduced. When they give electrons to something, they become oxidized because they've lost electrons and they reduce something else. So whichever molecule lost electrons becomes oxidized, whichever molecule gains the electrons becomes reduced. So the name of these electron carriers are NAD+ and FAD. They are carrying electrons that have been, usually they're carrying electrons that have been stripped from sugar or some other food molecule. In their electron poor condition, they exist as NAD+ and FAD. When they are carrying their electron load, they exist in the form of NADH and FADH2 because they tend to pick up protons when they pick up electrons. I am never going to ask you to track protons. Protons, hydrogen is just a proton, right? So that's where the H comes from. It's hydrogen for proton. I'm never going to ask you to track the hydrogens. I know that a lot of instructors ask you to, but it's really just not that important. It's not the main point. The main point is where are the electrons, because it's the electrons that are carrying the energy. Okay, so all you need to know is that if you see NADH, it's loaded up with electrons. When you see FADH2, it's carrying high energy electrons. But when it's lost its electrons, when it's empty of electrons, it exists as NAD+ and FAD. Right. So this is just a diagram of a redox reaction. You have oxidation. Redox. It's called redox reactions because they happen together, of course. When an electron is passed, you always have one molecule being oxidized or losing the electron and another molecule being reduced or gaining the electrons. So here's an oxidizing agent. An oxidizing agent is a molecule that oxidizes other molecules. So this molecule is becoming reduced. The oxidizing agent is becoming reduced by stealing the electrons from this other molecule. So here you have the oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And then here's just one more diagram of a redox reaction. So you have some organic molecule. It could be a sugar. It could be a fat. And it's got all these unstable, high-energy electrons because of those unstable electron configurations. And those electrons get passed to NAD+. Well, this molecule, the organic food molecule, has just been oxidized. NAD+ has just been reduced and has become NADH. Okay, so that's a redox reaction right there. All right, phosphorylation. So here's substrate level phosphorylation. That's super easy, right? You have, all it is a phosphate group gets added directly from one molecule to another. So here you have a phosphate group, perhaps in some food stuff, and you've put it on ADP, adenosine diphosphate. Di means two. So this is the same, this is the ATP molecule, but with only two phosphates on it. So this is adenosine diphosphate. It's the ATP molecule, but with only two phosphates instead of three. And here's a phosphate molecule and some food stuff. So you take this unknown molecule with a phosphate group, just add its phosphate group to ADP, makes it into adenosine triphosphate. Tri means three. So now you had two phosphate groups, now you've got three phosphate groups. And this molecule is now changed because it's missing its phosphate group because it's added it here to create ATP. That's substrate level phosphorylation. Phosphate groups attached to organic food molecules can be transferred directly to ADP to form ATP. And that happens in some steps of metabolism. That is one of the ways that we make ATP. It's not the main way, but it is one of the ways that we make ATP, which is our, remember, energy currency of the cell that then carries that. Now there's a lot of energy in ATP, carries that energy to all the places where the cell needs to do some activity. In oxidative phosphorylation, also I prefer to call it chemiosmotic phosphorylation, high energy electrons are passed off to oxygen, releasing energy, and that energy is used to drive ATP synthesis. And this happens in the electron transport chain, and it's a many, many stepped process, and it's really complicated. I'll just repeat it again right now, but if you're not understanding it here, do not worry. There is an entire lecture about just this process step by step. I'm just giving an overview. So if you just know that this is the complicated part, we're going to get to it this week. So in chemiosmotic phosphorylation, high energy electrons, which come from your food, by the way. So there's these high energy electrons that were stripped from your food. Here they are down here. Where's my cursor? Here. High energy electrons that originated in your food. These get passed off to oxygen from the atmosphere. Okay, and as that happens, they release all this energy. A whole bunch of stuff happens in between, but they release all this energy, which is then used to drive ATP synthesis. So phosphate group plus ADP to ATP. Okay. This phosphate group is not coming directly from another molecule, so it's not like another molecule just gave it the phosphate group. There's a many-stepped process, so these electrons are providing energy to press a phosphate group onto ADP to create ATP, or two phosphates to three phosphates. This is a higher energy molecule, this is a lower energy molecule. So ATP is like the charged battery, ADP is the depleted battery. So it's getting charged up here, driven by the energy from these electrons. And there's a whole, there's chemical gradients, there's many steps in between that I didn't cover just now. Don't worry, we'll get to it. I promise you it will make sense. I know that a lot of you might remember with horror the electron transport chain from your past and how it was so complicated and you can't remember any of it. Do not worry, I promise you it will make sense when we get to it.